Hello, this is Ertan Taskin from Ozen Engineering, and in this video I'll be demonstrating the steps to generate a reduced order model for predicting the vortex formation in a stirred tank. So before doing anything, we will start with the fluent job that we have gone through in the previous work. And while saying that, I'd like to remind you that there is a blog in Ozen Resources website about all the initial steps, how to set the model, and corresponding input and output conditions, details, as well as post-processing the results. So in this work, we will use the same infrastructure, but we will add new items on it for the reduced order model generation. So let's continue with the workbench project. Since we have done everything in terms of the setting and the initial solution, let's take a look at the parameters. Meanwhile, we have 4 input parameters: density, viscosity of the fluid, speed, as well as the level of the liquid. So the output parameters, we have few dimension-related parameters, a torque, power, as well as the vortex depth. So in order to proceed, we have to bring the reduced order model generation module here from the design exploration and drag and drop to the screen. And when we bring this to this designated area, it will make an automatic connection with the rest of the project. So what we have to do, of course, we have to click here to open the design of experiment screen. So these are the major or the default selections. Optimal space filling design, meaning that the design of experiment will be created to fill a design space. There is no constraint to focus on only a certain region, etc. And the number of samples is indicated as 32. We have 4 input parameters, and the software utilizes 8 configurations for each. That's why we have 32. So what we have to do is actually we have to get here and update the design of the experiments. But before doing that, let's preview the corresponding configurations that software will choose. So these are the 32 conditions, as you see, different values of density, viscosity, speed, and the liquid level. All these sections are currently empty because the simulations haven't been performed yet. So I skipped, of course, the simulation part. Once the simulations have completed for all of these 32 cases, now we have the corresponding output parameters values that are already put here. So our design of experiment is completed. The next step is to create a reduced order model. So in order to do that, we're going to have to get here, and in this screen you see that there is an export ROM option. So when we click here, now we are given an option to choose in terms of the type of the file. So ROMZ or FMU. FMU can be utilized in the Twin Builder, so it can be imported into Twin Builder. ROMZ actually can be imported into the fluent. So we will continue with the fluent, and I have already saved the mixing tank ROMZ. So after that, the next step is to open a new workbench file. So once it opens, bring the fluent on the screen. On the setup, right click, import ROM, and that is actually my ROM file that I already generated. So I'll click on that. After a while, you'll see that the parameters are already brought up here. And what we have to do, we have to update the project in order to get the green check marks on the setup as well as the solution phases. Once all the green check marks are already received, we will open the Fluent session. So after the Fluent session opens, let's get into models and ready starter model here. We have two tabs here, setup and evaluate. And in this evaluate screen, we see all the 4 parameters that are utilized for the ROM creation with the corresponding ranges. So once we change the number within the range, we can see the impact of that. But before doing that, we have to bring a post-processing screen in front of us. For that reason, let's go to the graphics and contours. So when we get to the contours of section, we have to choose ROM related cell functions. And from them, we are after the water volume fraction contour. And when we save and display, that is what we see for this particular operating condition. Now, what I will demonstrate here, if I make a change on a different parameters, I will be immediately seeing the impact of that on this corresponding contour, such as let's reduce the speed, and the impact of that will be quite significant, as you see. Don't worry about this error, that has nothing to do with the ROM part of it, but as you see, the vortex is not as visible. Whereas if I increase and crank this to all the way to the highest speed, we will, oops, sorry, I made a mistake on clicking a wrong button. All right, let's make this 30 again and hit evaluate. And as you see, now the vortex is visible. So we have options of course, looking at the different parameters. One might be interesting in to take a look at the liquid level. So let's drop the liquid level to one of the low options. Yeah, the liquid height dropped, and that definitely impacted the size of the vortex. And let's increase the height to the maximum. And now you see, when we have more fluid, even with the highest speed of the current study, the vortex is pretty much eliminated. So as you see, this is a very good tool to explore all different kinds of combinations and see the impact of that immediately after, of course, you generated the ROM with the design of experiments. I think this is all for this video. Thank you for watching.